We'll go back to my office. Just wait for some ice cream.
Oh, nice.
Yeah, I do a little bit of work.
No. This we wash it and
Oh, okay.
we don't throw any of this stuff away.
I want to watch this.
Just hope it doesn't end up in the refrigerator like that quiche did for 3 weeks.
Sorry?
There's still quiche in there from Thanksgiving in the refrigerator. I think maybe somebody finally threw it away, but yeah. We had quiche for Thanksgiving and then it's been sitting in the refrigerator.
Yeah, I'm pretty much, I may take off a little earlier in the afternoon, but that's not full. For the frequency, the one that has been. Yeah. Okay.
Our colloquium speaker today is Ron Allen. Ron is a man who needs no too little introduction here in Green Bank, but we'll give him one anyway.
It usually means something bad.
In all the positive ways. So Ron did his undergraduate at University of Saskatchewan, his PhD at MIT, and has been on faculty and a professor at various institutions. Right now, he is at the Space Science Institute and Johns Hopkins. He is going to be talking with us today about some Green Bank Observatory work on OH, and he's also brought his student Michael Bush with him. Michael will give a lunch talk tomorrow up in the Drake Lounge if you can join us for that. With that, I'll let Ron take it away. If you do have any other questions throughout, I've been told to tell you to interject, make yourself known, and if you have any larger discussion questions, we'll save those for the end. So with that, thank you, Ron.
Thank you. So this is sort of becoming an annual affair. Julie just reminded me that it was October of last year when I gave the last progress report, so I should clearly have used a different title because it is in many ways a progress report of where we are now. Some of you will remember some of the things I spoke about last time when you see the slides flash by. I've expunged a lot of the older material thanks to Michael. Best thing to do with your presentation is run it by your grad student and he will tell you what to throw out because he already knows that stuff, so that's fine. So I'm very happy to have the opportunity to bring you up to date and where we are with the OH work that's been going on here, thanks to the efforts of quite a number of you. And I'm going to then go immediately, because I know you're all busy. I never cease to be amazed at what a beehive of activity is going on around here. People never seem to have enough time. So I'm going to cut the history fairly short. The participants in this work have changed only in minor ways. Myself and Dave Hogg essentially remain the initiators of this. And graduate students include Philip Engelke, who is now Dr. Engelke, and he's back in the Boston area. And Michael, who was earlier introduced, who's just picked up the mantle and is running with it now. And here at the GBO, it's largely through the efforts of Frank Igo that we've managed to make progress in especially using the 20-meter telescope, which I'll come about in a little while. I'm going to tell you about current projects that are going on. I'm just going to summarize briefly the nature of the progress report. Then I think I want to spend most of the time, the last half of the talk, talking about these very curious things that we've discovered that we are calling the OH pedestal in the galaxy. And I'm not sure if I said anything about it last year. I probably didn't. That we were quite convinced in that time that it was an instrumental effect. And we worked hard to show that it was an instrumental effect and it would not go away. And in the end, we've come around to the fact that this is showing us large-scale structure of OH in the outer galaxy. And I hope to convince you of that near the end of this talk. Okay. So why is OH such an interesting thing in our view? Well, the reasons are quite simple, actually. These L-band lines were found, of course, first in absorption against continuum emission of Cat-A. That's how they were first discovered. And the big surveys that were done of the galaxy were largely all done in absorption. The emission surveys, of course, centered on studies of the maser lines. And OH masers were found near H2 regions for very good reasons, because they're pumped by infrared radiation. But the general interstellar medium is not a place with a whole lot of infrared. And what kind of emission you see there is just standard, shall we say, collisionally excited emission of OH. It's very faint, but it's everywhere. And you can detect it, and we have, in the two main lines, by and large, are the ones we focus on. And it's pretty well always in LTE. It's collisionally excited, so it's not surprising that it should be in LTE. And we have, in fact, Michael, as part of the first work he did, has done some very careful analysis of calculations which show, using codes that are available, to show that it's largely a density effect. And we're able to see OH in regions of very low, and I mean really very low density, typically like H1. And so it's probably for that reason that the best comparison of what the galactic distribution of OH is like is probably going to be H1. The difference being that the H1 is largely optically thick everywhere, as I'll remind you. And that's not the case with OH. So it's a molecule. You should be interested in it. And they're optically thin, these lines. Nothing to do with masers. Everything to do with standard excitation by collisions and by radiation in the interstellar medium. So not weird stuff, standard stuff. And the connection, as I say in the end here, to column densities and ultimately column densities of H2 is dependent on how well we understand physics. And the physics is not wild, it's not weird. So we just have to do some measurements and be careful about what we do. The calculation, going from column density of OH to column density of H2, is also something that you can measure, because the ultraviolet absorption lines of both tracers have been studied in considerable detail in interstellar medium. And there is a linear relationship between the two, which is quite astounding. So if you measure column density of OH in the radial, the L-band lines, you can determine the column density of H2. And this is a direct way of doing it. And there's little controversy about what's going on. Yes?
How strong is the OH compared to CO?
Can we defer that to a little later? Because we do have comparisons with CO. I'll give you the short answer. Okay? The real answer for CO is that it's a high-density tracer. It requires densities of typically 1,000 times higher than the densities we need to excite OH. So it's very good in places where you squash the gas together for whatever reason. star-forming regions are a good example. Squash the gas together with, stellar winds and exploding things, and the CO shines. But actually OH is there everywhere, and it's always visible. So you don't require this curious, if you like, feature of CO that it's so dependent on the volume heads. We'll show this in the end because Michael has made a very nice comparison of these two. We studied this question in some length, which I'll also mention in a moment. I just want to remind you that H1 in galaxies is largely optically thick, and the example I like to use is some work that was done by one of my recent grad students, Stephen Peters, along with my colleagues Tana Crowder and Freeman. And he got interested in trying to model, this is a good example, he learned a lot about computer programming and wanted to model how the distribution of gas was in a galaxy so that he could look at the kinematics and study the dynamics of galaxies using that. He came to me first to see if I would help him with this, and he showed me these beautiful pictures that he had from the Australia telescope of H1 galaxies. So these are just what we need. Tilted like that, you can study the Z distribution, use the velocity field to study the depth and so on, and we should be able to get the 3D distribution of all the kinematics and the dynamics of these galaxies. I said, that's fine. I said, now would you first, before you do anything, take those plots that you're showing me and convert the surface brightness coordinate units, which you're using, from millijansies per beam to Kelvin. And he looked at me rather puzzled because as a student he'd always been handling data other people had done, and everybody does all of these images in millijansies per beam. That's what comes out of synthesis telescopes. It's a travesty. It's a travesty. So he did, and this was his first paper. We find each of the galaxies has the same maximum surface brightness. Shouldn't be surprised. And the self-absorption is the main cause, and subsequent decomposition will require a treatment of this. And it did. And he never did it properly because he couldn't. You didn't know what the actual distribution, you had to know what the distribution was in order to calculate it. So this was not a non-starter. So he gave up in astronomy and went to be a quant. You know what a quants are? They make, I understand, the latest value that Michael suggests to me because he's toying with the idea of self, I think. It's about our combined income per year multiplied by a factor of 4 or 5 or something, and that's their annual salary. So it was a lost cause from the beginning. But we did get several papers on it. Here's the story. One H1 galaxy, beautiful picture in the sky. Never mind the units, we know that this is not the units we want. This plot is the units we want. It's the trace along the axis. Of course, we shouldn't be surprised if the answer is about 90 Kelvin, because that's what we find in the galaxy too. So that's going to be the story sort of behind the reason for looking so very carefully at OH. Even in the case of H1, even if it looks similar to H1, it's going to be different because it's optically thick.
What's plotted here?
So this is the surface brightness along the axis of this galaxy in brightness temperature.
I mean, but at what velocity?
The whole thing.
The maximum
brightness, temperature in the spectrum, and
This
everything.
is integrated. This is just an integrated amount.
Well, it's integrated is not TB, it's,
Yeah.
You think it should be TV delta V? Is that what you're saying?
yeah, I mean, at each position you get a spectrum, and you're turning that into a single TB.
Well, right, yes.
And the transformation is the peak of the spectrum? The brightness temperature of the spectral peak?
It would be the peak of the spectrum.
Okay, thank you. No secret channel.
Correct. Okay, we'll move on here. We had some initial results, which you would remember, I think, from previous talks. We first did this blind survey with the Onslaught telescope and discovered that OH in the galaxy is ubiquitous. Then we did our first pilot survey using the GBT. And I won't spend any time talking about that because we've done it last time. But what I would like to remind you is that we tend to limit our studies to the outer galaxy. And as I've explained on several occasions, there's two reasons for it, but one very good one. The first one is to try to avoid the velocity ambiguity that you get along lines of sight inside the solar circle. But a far more important effect in the case of OH is to minimize the confusion that comes from radio continuum, because as we look into the inner galaxy, we have a lot more radio continuum to contend with. Because OH excitation is very sensitive not only to collisions, that's the density of particles, but to photons, the density of photons, because they interact with photons as well. And they can excite or de-excite the transitions, which means that you have to worry about the ambient. Obviously, there's the 3 Kelvin, the 3-degree background all the time, but in the inner galaxy, it can climb up to be quite large values. And they essentially destroy your ability to understand exactly where this gas is along the line of sight, because it can turn emission profiles into absorption profiles through nothing except changing the place where the gas is. If the gas is in front of the continuum, it'll look like it's an absorption profile. The same amount of gas is behind the continuum, it'll be an emission profile. So that's the whole reason for avoiding the inner galaxy. We're just avoiding it until we've understood what's going on in the outer galaxy, and then we'll move on. So this is typically a line of sight, and let me point out to you that we're going to be looking at data around more than one. This is sort of the spot where we started, about 108. Never mind why it was 108, it just was. And we've studied the whole situation. We're moving toward the anti-center point. And the reason for that will be clear in a moment. Okay, another nice thing about the outer galaxy is that we have distance information provided by triangulation. That is the Bessel, the Bessel collaboration that have used VLB techniques on high mass star forming regions in order to measure by triangulation, essentially using the base of the orbit of the Earth to tell us the tiny little parallax of these major sources in distant star-forming regions. So we know what the distances are, and we're quite sure in parsec. So we can take a radial velocity, as well as we know that, and map that into a distance from the sun with significant accuracy. And that's important if we're trying to understand the physics of these regions. I'm not going to say too much about this first blind survey, except there were 27 pointings in it. And perhaps the most interesting result that came out that we followed up was the fact that a good number of, this is the carbon monoxide profile integrals measured from John Dane's survey in the galaxy, and versus the OH profiles. What you see here is we've segregated data into two blocks. The open circles are data which is statistically well above zero for CO. All data in the plot is above zero for OH, because the OH was much more sensitive than the CO. And there's sort of a correlation diagram here in half the data, and the other half is just noise. And I've colored this black because this has gotten the moniker of the CO dark gas. And indeed, there were error bars in OH, as I said, were very small, but they were larger in CO, and that led to some complaint from the CO community that we used a noisy survey and we should have done a better survey. Well, so then the next thing we did was analyze similar data. Michael did this work in a 1 square degree sample of sky using CO data from the 5 College Radio Observatory survey of the northern sky. And that could be made very sensitive in the same beam size as we were using for the GBT observations. And finally, what came out of that is shown here. This is from Michael's 2019 paper. This is the old data from our 2015 plot from the first survey. This is the new one, but we have to look only in this area here because the sensitivity of the CO data went way up. And so, of course, we said what would happen. We predicted what would happen. Namely, if I go back, we predicted that what would happen was these points the error bars would collapse. But they're not going to move in the diagram. They're going to stay where they are. And that's exactly what happened. Because they showed the diagram, still it's the same kind of structure, right? There's a correlation, and there's a bunch of 0 points here. So it's just a lot more sensitive, but the answers were the same that we knew in 2015. Namely, that there is a dark component of interstellar gas that is CO dark. You don't see it in CO. And the reason for that will become obvious in a moment. Okay, so one of the interesting things that we did with the first grad student worked on this, Philip Engelke, was to study a star-forming region. It's a popular, shall we say, conventional wisdom. The star-forming regions are what they are and where they are because the density is higher. And if you poke at that question and say, well, how do we know that? The answer everybody gives is, oh, well, you see the carbon monoxide there. And that's a molecular tracer. And you don't see it in the interstellar medium. And so it's not there. That is, there's no molecules on it. And yet we were seeing molecular emission everywhere. So how does it look if you focus on the star-forming region? And the choice was W5. That proved to be a very lucky choice. So I'll explain in a minute. It's a star-forming region, an H2 region with a fairly large area of the sky compared to the GBT beam. It's many, many GBTs beams big. And Philip did I would say, a mapping of about half of it using the GBT in two different chunks, and looked at very carefully what was needed for that. Well, the first thing that was needed that we didn't have when we went into that study was a way of calculating reliable column densities of OH. For those of you that remember your radiative transfer, you need to know not only, the integral of your brightness temperature profile, dV, but you need to know the excitation temperature, Tx, right, in order to make it into a column density. And Tx wasn't particularly well known for OH, not for the kind of OH we're studying. W5 proved to be an absolute godsend in that regard. And the reason is that, as luck would have it, the surface brightness of the radio continuum in that nebula is very close to the excitation temperature of CO. How did we know that? Because in some places we could see OH in emission. And just a little bit, arc minute further away, it was in absorption in the same velocity. How could that be? Well, the continuum temperature had changed. It went from small to large. And in the large, we were seeing it in absorption. And where it was smaller, we were seeing it in emission. So all we had to do was look at the value of the surface brightness in the radio continuum at the point where it switched over. And that gave us the excitation temperature of the OH that's in front of the nebula, of course. It's not in the nebula because the nebula is ionized. And it would be O and H, but not OH. So we know what the answer is to that. And the answer was, interestingly enough, an old conjecture that had been suggested by Dick Crutcher, that the excitation temperatures were not the same in the 1665 and 1667. And indeed they're not. They differ by a degree, almost a degree. But if you use the right excitation temperature, you get exactly the same column densities. And if you don't, you don't. So I think we've got that one nailed down. So we knew the excitation temperatures. This allowed us to calculate the mass of molecular gases because we could convert using the UV conversion factor. And what came out of this was rather astonishing. That in spite of this idea that CO is telling us where the molecular gas is, we were seeing as much of it in OH and more. It was about twice as much in OH. But there's actually no real difference between that and the general interstellar medium. This is a paper which Philip is currently writing right now. Because we can measure it everywhere, and in Michael's analysis of the 1 squared degree, which is just a quiet field without star-forming things, we see very similar amounts of molecular gas per volume, per cubic parsec, if you like. So there's something going wrong in the star-forming regions. They start in some way that surely has to do with, the collapse of clouds. But once they start and stars begin to shine, somehow they mess up the interstellar medium around them and create these dense pockets. And the dense pockets show up in CO. This is a conjecture that we're trying to right now follow up on using CO syntheses of gas in certain regions of W5. And the next thing that I wanted to tell you, and we can look at this together, I should maybe even give the floor over to Michael because it's got his stuff in it, is what happened with the quiescent region. So we took this square degree where there's nothing unusual to be seen. No H2 regions, no infrared sources. It's just kind of very, very dull region. Nobody would bother looking there for anything interesting. So we said, good, we're going to look there, and we're going to do very sensitive OH. And sure enough, in this 1 square degree, we showed up quite a lot of OH emission and very little CO emission. And we teamed up with a couple of theorists, one in JHU, David Neufeld, and a colleague of his at Maryland, Mark Wolfire. They had a code to do calculations of these things. And so with this code, they computed for us what the models were. You remember that diagram? I'm going to go back to it just briefly. This one here, which has this axis here of OH line flux down here and CO line flux up there. That's an observational diagram in which I can plot the data points. They can calculate that within the context of their diffuse ISM models. And that context produces this diagram. And you see that there's these 2 parameters that are in their calculation. The volume density and the path length, which is measured in AV, because that's the way somehow these folks like to think is in AV. So if you put in the volume density and you put in the AV, it'll calculate a point on here. And if you do a grid, it's a 2-dimensional thing, and essentially it maps onto the column density in OH and in CO in a funny way. So it's another 2-dimensional grid, if you like, laid over top, but it's not a nice, neat, it's all munged up. So it's squashed in various funny ways. And this is what the funny ways are. So you can see along here, these numbers are in volume density. So high densities in volume are up there. Low densities are down here. The data points are here with CO and OH plotted together. And what you can see is that there's all my upper limits of CO are here, below this limit here. With the possible exception of 1 or 2 points, there's one that seems to be a little bit just at the top end of it. And so what's happening is that as you go from high volume density to low volume density, suddenly the CO disappears. You can only recover it by moving to higher values of AV, path length. This is sort of reasonable, right? Because if you're going to low density, what you're doing is the collision rate is too slow to keep CO from dropping down into the ground state. The CO molecules are being kicked by collisions with molecular hydrogen. And they're kicked frequently enough. There's a whole bunch of them up in the first excited state, and they drop down and they emit photons, and we see them. If you turn the density down in the model, the volume density, the number per cubic centimeter goes down, and we get to the point where there's not enough collisions to keep the thing pumped up, if you like. So you excite the molecules into the upper state, and before you know it, they're back in the ground state, and there's no other H2 molecule nearby to kick them back up. So the result is that everything's sort of sinking into the ground state as you go down in density. But there's still going to be a few molecules in CO excited. one or two, sort of, not too much. But if your path length is long enough, you'll see. And so that's why the other parameter in this is AV, essentially the path length. With very large AVs up in this direction here, you will get them back. So that's why this point shows up as a detection. And anything that would be up here would have been also a detection. And so I think this explains quite simply what's going on with CO. And I hope that you can see that it's not too difficult to understand why CO is not a particularly great tracer for the interstellar medium, especially the diffuse gas. Okay. Oh my God. All right. I talked about the critical density already, and this is just a calculation that shows it. Basically, the critical density depends completely on the Einstein A. It's the ratio of the Einstein A, which is the decay rate, to photon decay rate by radiation, to the excitation rate from collisions. And if one is bigger than the other, then collisions will dominate and keep things going. And if the AV is too large, if the Einstein A is too big, everything will rain down into the ground state before it gets a chance to get kicked again. The Einstein A for CO is 10 to the third times larger than the Einstein A for OH. So the critical density is 1,000 times higher. I don't think we should be surprised that in low-density environments, no volume density, we don't see CO. It's very simple. Physics, I think, is quite simple. Okay. So that we'd like to know, now that we understand, I think we understand the physics fairly well. We're asking ourselves, well, what's next? What would we like to do next? And I think because OH is a radial line, we can see it at great distances in the galaxy. We should be trying to use it for galactic structures. And I'm sure this is what Jan Oort thought when he was pushing to find out how we might detect H1 in the mid-50s. And I think OH is essentially our molecular equivalent of H1 in that regard. And so the question is, what about galactic structure? Our entire picture of the structure of the galaxy in gas comes from H1. And then we chase after other things like H2 regions and so on. But ultimately, what we understand about the large-scale structure of the galaxy came from surveys of H1, done with a 25-meter dish. And that's how the whole structure of the galaxy became evident. Spiral arms, all the rest of it. We have here an optically thin tracer for molecules. We should certainly try to use it for similar things and see what stuff has been missing. We've been missing because we've only had this one tracer, if you like. We've had only one game to play. Now I think we have another game to play, and we're going to try to see what kind of results it brings up. And I'm going to show you in the last bit of time I have. There's a couple of things I should mention, because these are things that also, I mean, we have data on some of this already. And the thickness of the gas layer is a problem that Jay has worked on using H1. And it's a reasonable question to ask, well, what does it look like in molecules? Well, there is an answer for CO, and the answer is not very interesting. It's very thin. I suspect that's probably wrong. And when we actually do the experiment in OH, we'll find a different story. We have studied in rather great detail here, using the GBT, the distribution of OH in the Perseus arc. which is the nearest spiral arm in the outer galaxy to the sun. And what was found was that the Perseus arm has this funny, this is a velocity latitude plot from the 140-foot telescope taken by Butler Burton about 1,000 years ago now. And he did the whole distribution of it in the northern hemisphere. And what was found was corroboration of something that was discovered in the 50s, frankly, or 60s, was that the H1 in the Perseus arm appears to be rolling. First of all, it's thicker, and it appears to be rolling. It looked like part of it, the upper part, is coming toward us or going away, I'm not quite sure what, and the other lower part, that goes in the other direction. So it's like rolling. The arm, this is a diagram of it that was produced by Wan and Wallace in trying to explain this. Their explanation was that, well, it's got nothing to do with dynamics and everything to do with geometry. And it's because of the tilt of the warping of the galaxy in the upper part, which by that time was known and fairly well understood in terms of H1. What about the molecules? CO has been more or less a no-show here. Well, every red dot is the detection in the Perseus arm in OH. And as you can see, it's got the same sort of kinematics as H1. But now we can measure those clouds, if you like, with great precision and look to see what's their distribution. And does it actually resemble what you might expect from H1 or from something else? Because the stars don't do the same thing. And so that will be a focus as far as the structure, large-scale structure is concerned. So we have that data already in hand. What's next? Well, in 2015, we made a serendipitous discovery. One of the profiles that we were looking at, one of the directions in the galaxy, showed up a curious feature in OH. And we found it simply because we took a whole bunch of data. We had extra, thanks to the abundance, thanks to the rain, which by the way, Will, you always sign your email say, "Clear Sky." For me, would you please sign it that says, "Rain." Please rain. I love rain. That gives us a lot of time on the GB. So thanks to rain, we had some data, and we could stack it together. So instead of usual 2-hour observations, which I've been displaying to you so far, we normally observe for 2 hours with the GBT at a given point. We had about 10 or 11 hours of it. And we put it together just for fun. And up popped not only local gas, Perseus arm gas, outer arm gas, but a pedestal of emission. Now we initially described this pedestal to an instrumental effect. We thought this can't be real, it's got to be wrong. And I've spent the last, well, probably 3 years trying to show that it was an instrumental effect, and I failed. And I'm going to review for you now how we did that in the last several years. This pedestal, you should have a diagram here of it. You've got one in your slide set tomorrow, which shows the original 10-hour profile in which we saw this pedestal. We have now, it shows up in both transitions, 1665 and 1667. It shows up in 2 different telescopes. We've seen it in the GBT first, and we've seen it thanks to Frank Gigo and his help in the 20 meter. And we've seen it now in several different pointings. So it wouldn't go away. And the only thing that we were doing the same every time was reducing the data in GBT IDL. Thanks to Frank. And so we began to suspect. I showed these results to Ron Eakers, and he said, well, you're still using GBT IDL for all. Maybe there's a bug in the software, in the baseline fitting software. Well, yeah, that could possibly be true. So one of the first things we did was try different subtractions of baselines, like bandstop filtering. So I went and calculated transforms of the lines, turned them back into periodograms, threw out the low order periods, and reconstituted. So it was a pure Fourier filtering trick. That turned out to succeed on the one hand, to fail miserably. It gave me a flat baseline, but the signal was in a bowl. Of course, I'd set the zero frequency to 0. So the integral of it was going to be 0 for sure. And I had to fit a polynomial anyway at baseline in order to bring it back up. So that was a non-starter. Now, Michael will tell you tomorrow how to do this right. And it's a bit surprising. Here's 2 transitions with the GBT, showing you where we are now. This is local gas. Velocity is going out towards the outer galaxy, 150 kilometers a second. That's like way out there, where the H1 is beginning to tail off. And we have an emission feature. And I've tried to convince you that this feature will not go away. It just stays there. 1665 is less convincing. Of course, the transition is only half as strong anyway, to start with. And that means that we're even more sensitive to our ability to get the baseline correct. I don't think it's any longer a question of instrumental effects in the baseline determinations, but there is a precision problem. The signal's too weak compared to the amount of time we're spending in integration, and we have a precision problem. So that problem persists. So we can see it out here, but we don't see it in here as well as we'd like. That's the bond H1, which is essentially the same as you get with the GBT after correction for stray radiation. So both transitions are showing up. This happens with the 20-meter telescope as well. This is a lousy picture to show this, but it shows up top here 2 different pointings with the 20-meter. And you can see the pedestal there as well. That's it, right there. At 2 different pointings, and they're separated by well over a beam width. And this is the 20-meter. Well, you know right now that this feature is large on the sky. It's a large structure on the sky. And these are the 1665, which from the 20-meter is even poorer signal still than with the GBT. It's a large-scale feature. We've established that we can't get rid of it by messing around with telescopes or messing around with receivers. It keeps coming back. So we decided to start looking for features for the signature of a large-scale feature. Not just a blob sitting in the sky out there somewhere, but something that really is a part of galactic structure. And so in the most recent DD proposal, which the director approved, we did little visits along the galactic plane from where we started at 108 towards the anti-center. Now, this is what you'd expect. Oh, I'm first doing latitude on it, that's correct. So if it's a thin sheet, as we began to suspect, we should be able to go down and up until we run out of it. Well, going up didn't help. We went up to 5, and we plus 5 degrees, we still see it. But it disappeared at lower latitudes. And the reason for that is probably because that's what happens to the warp of the galaxy. So it's got the signature in latitude of the galactic warp in H1. Well, so does it have the rest of the signature of H1? And so, what is this behavior with longitude? Well, this is an H1 collection of all the data in the galactic longitude versus VLSR coordinate system. This envelope here is called the terminal velocity, because there's no gas beyond that as far as galactic rotation is concerned. Anything beyond that isn't taking part in simple galactic rotation. Okay? We have data first at 108. We did 138, 158. I want to show you the 2 terminal ones here, about what that looks like. And for now, I want you to focus on the H1 up top, because that's really what's telling us. We know H1 is a large-scale feature. Nobody doubts that. What you see here is that at 108, where we started, the stuff is available and visible out to about minus 150 kilometers per second. That's that part of the curve. Going towards the anti-center, at 138, it's come down to about minus 110. And at 158, it's about minus 75. If we would continue going to the anti-center, it all sort of bunches up, right, to where it's all piled up at 0. And you don't see it piling up in H1 because the H1 is already optically thick. So it's not going to get anything brighter. But the OH will. And indeed what happens is, we get here, this is the 1667 GBT spectrum. This is, how many hours, Michael? 10? Yeah. And there's the pedestal. Moving around to 138, it's not 108, 138. It's there, but it's clearly fainter, and what's more is it's pulling in velocity. And here, at 158, it's just a shadow of its former sun. It's behaving like H1 in the large scale. So this is a summary. These uncertainties in the baseline fit were of enormous concern to us when we first ran into this in 2015. And as I said earlier, I initially expected very strongly that it was an instrumental effect. We've looked hard at that. And the answer was no, it won't go away. And I would say that several years of study and experimentation with the GBT, which was thanks to these awards which were so generously provided on Open Skies time with the GBT. And the 20-meter data, observing time, large amounts of it, financed not by the NSF, but by the Space Telescope Science Institute director, have allowed us to get to where we are. So with current data, I think the molecular pedestal has a distribution very similar to OH, confirming that it's a large-scale structured feature. Unfortunately, residual baseline uncertainties are still limiting our ability to make precise measurements. And I'd like to make precise measurements if possible. So we're still working on that, and Michael will go on with that tomorrow. That's it. Thank you. I don't know what I'll do for an encore. It's 2020. I'm not sure.
All right, so I'm 50% convinced. All right.
Oh,
50%.
50%. That's a big advantage over what it was a year ago.
That's better, right? So, I've got a couple of suggestions on how to get to the other 50%. Okay? One of the things you try, so there's two instrumental places in which you can get baseline shapes. One is at RF, and one is at IF.
Yes.
Okay. So one of the tricks you can perform in our IF system is you can specify in your configuration an offset frequency.
Yes.
That will shift your line to a different place in the bandpass. Instead of line being the center of your bandpass, it will shift to the end. So if the lines are still there, that means that it's an RF. Okay. But if the pedestal isn't there, it means it's an IF.
Simply each of the IF.
Yeah. Okay. All right. So that's one way to determine whether it's IF or RF. Now, to determine whether it's instrumentally RF, one way to do that is, instead of looking in the second quadrant, where the pedestal is at negative velocities, if you went to the third quadrant, the vertex arm is weaker, etc. So it's a much more difficult experiment. But if you went to the third quadrant, the pedestal then becomes at positive velocity. It completely changes what part of the RF spectrum the pedestal will sit. So if it sits at both negative and positive on both sides of the
Isn't that the same test you just told me about? By shifting them.
No, that only shifts the IF. The RF stays the same between the two outputs. By doing the offset frequency, the RF,
you're shifting the RF.
So in order to shift the RF, which you can't do because that's nature, you have to shift the geometry of your observation. So if you look at the third quadrant, then
What about the 1665? We see it there too.
yeah, no, that's what I'm saying. 50%. That's it. But it also, when it's strong in 1667, sometimes it's not there in the 1665.
Well, it's a solar noise issue, and as I said, it's the precision with which we can do these baselines.
I agree.
But I'm listening.
All right. So changing the quadrant and still seeing it means you're looking at a totally different RF spectrum. Right? If you want to see it, it has to be something that is probably then not telescope related. But those might be suggested ways.
What about these, that's also part of the 50% positive, I suppose, that it has the latitude, the longitude.
Right.
The 20-meter spectrum, that's also part of the 50%?
Yeah.
Okay.
Yeah.
It's clearly anything we can do to improve the precision.
Right. Because, I mean, if there's no OH is out there, then that means that there's, as you've implied, that much H2 between the spiral arms.
Yeah.
And that much H2 would have been, I thought, would have been detected in things like absorption experiments. And optical absorption experiments, right?
Well, the trouble with you mean
UV absorption line.
No, the trouble there is distance. You can't get more than about a kiloparsec from the sun with those absorption experiments. You run out of signal.
For extragalactic objects.
Well, you run out of signal to do the UV absorption.
Right. I don't know whether or not you have enough signals. Right. Or with the H2 that's between the spiral arms.
So you're suggesting we would do an absorption experiment using a radio source.
In the UV. Like Copernicus. Let's go back to the old Copernicus data. This old Copernicus data showed H2 existing between the spiral arms.
Okay. I didn't know that.
I don't know. That's why I don't know. What?
So that's worth looking at.
How much mass and
Right.
H2 is there based on your...
Well, the fact the galaxy is turning molecular as you move out is the implication of this. The H1 is dropping faster than the H2. And so you're...
Right now, I wouldn't say that I wouldn't go so far as to say that. I think what we do see is that they're essentially co-spatial.
Well, you're looking at the velocity extremes. If you took the ratios of the lines, then you would see that OH over H1 was increasing as you went out.
I think that's true.
It could be a function of the UV field.
Yeah. I think that's UV field.
Yeah. H1 is a sort of dissociation product of H2 as well.
I mean, you're trying to answer a question that's into the 70s and 80s. Is there molecular material between the spiral arms?
The
answer, you say yes.
I did.
Okay.
Yeah. But I have a question, how much?
But for the last 30 years, no one has said the contrast is much higher than what you're finding.
So how would you like the answer? At what units would you like the answer?
And
I would like to know the
versus mass of H2 as probed by OH.
Well, so here's what we can do easily. Because thanks to the parallax measurements and the structure of the galaxy we know in kiloparsec, we can translate velocity, linear velocity, into distance. Now, so you can then decide, okay, suppose we take the column density expression, which involves the excitation temperature and an integral over TB and so on, but it's TB dV. Differentiate that sucker with respect to distance. Well, then instead of column density, you've got volume density. And you have to put in the actual slope, dV ds. But we know that from, now we know it. I mean, we didn't know it, 20 years ago, but now we know it. What's dV ds for the galaxy in any direction you like? We put that in. Now I can calculate the volume density at any distance. 7 kiloparsec from the sun in the direction, typically 108 here. The volume density, what would you guess? 7 kiloparsec from the sun. What do you think the molecular volume density might be?
Molecular based on
OH.
Well, anything you like. Do it with, use your best guess right now. CO, whatever you like. What do you think would be?
For molecules, H2.
Molecules, H2.
Except for your pedestal, there's no data to put in the numerator.
Well, exactly.
Yes, 100.
No, what I'm saying, I'm sorry. There's data, and it says 0.
Yes,
Yeah.
maybe. I mean,
Plus or minus.
since we don't have absorption data everywhere, we're not sure, but it would be small. Right?
Yeah.
The answer is of order 100 H2 molecules per cubic liter.
I mean, that matches what your chemistry model is showing.
Cubic liter,
Cubic liter.
Per liter.
not centimeter.
No,
Liter.
that's really small. But that's not what your chemistry model.
Wait, did you say 1,000 or not? Isn't it like?
It does, yeah.
No, you get particles per cubic centimeter.
It doesn't matter. If I drop below that limit, I told you that if the path length's long enough, I can see it. These are parsec path lengths.
So you're saying 100 H in H2
100
per
H2
cubic
molecules
so it's
per
negligible.
liter.
It's very negligible.
And it's got a negligible.
There's no mass.
Well, there's also no opacity in no dust opacity. So you're being fried by the quasar's ultraviolet. I find the implications of that to be the strangest part of all of this.
Yeah.
That you're in places where you really do expect to see a greater degree of ionization and molecular dissociation, you're getting just the opposite.
Exactly.
Yeah.
I think the UV photons are all used up by the time they get there. That's probably what's happening. The only thing that we do see is B stars. We were talking about this earlier. There is a population, a loose population of B stars in the outer parts of galaxies, as evidenced in the satellite data. UV imaging. And that keeps some gas, if you like, neutral. It kills some electric gas. But apparently not all of it. I mean, I'm not saying it's as reasonable at first sight. I'm just saying we need to talk. Thank you.
Discussion, any other final questions? If not, we could discussion. All right, we'll have a discussion afterwards. Let's thank Ron again. And if you're interested in dinner, stick around. There is some discussion about Elk River or others, but if you're interested in dinner,
Not open.
well, then that kills the discussion. Okay, 13 minutes.
Would be detectable or HS2? It's not allowed.
And
That's what I wanted to know.
cosmological ratios are not really related to yeah, whatever, but high ratios.
So what you asked,
Far away from
when we detect,
yeah, can we detect? Yeah, characteristics.
in fact, Michael and I have been doing some calculations. Up till now, we tried.
Okay, what's nearby?
Well, why not?
Yeah, okay. It's not a cosmological relation from my perspective. Yeah. It's a good thought.
And we failed. But this was years ago.
Yeah, but
we
it was-
didn't understand all of it.
And there's also the problem of the beam, I suppose, no? No?
No, because the GBT beam is only 7 or 8 arc minutes. And of course, M33 is fairly big, so